Like me, you too must have studied trigonometry in high school and wondered what it was all about. They say it's about triangles, as the name suggests, because there is this word trigo, which definitely must imply three of something. So from the beginning, we all knew that it was about triangles. But wasn't it covered in geometry? If you need to find the length of the hypotenuse, you have the Pythagorean theorem, and if you need to find the area, the formula is quite simple, which is half times the length, the base, and the height of the triangle. So, what is the use of trigonometry? But the syllabus and the teachers and the upcoming board exam won't hear our argument, and they would go directly into teaching us about SOHCAHTOA. Basically, they are just formulas for sine, cos, and tan, respectively. What these acronyms say is that you can derive the ratio for sine, cos, and tan by dividing what they call the opposite side with the hypotenuse, then the adjacent side by the hypotenuse, and finally the opposite side by the adjacent side. All are respective to sine, cos, and tan, of course. It was fun for students like me who loved to think logically. So we jumped into finding the value of the sides, the angles, and then it progressively went on to prove the left hand side is equal to the right hand side. It was fun. It was deductive thinking at the best. But despite 4 years of engineering studies that involved high level trigonometry, I still didn't understand what trigonometry was about and what it was not about. It's like going to a vast lake and you don't know how deep is the lake. Also, you don't know where it starts and where it ends. However, if you look from a higher vantage point, you should be able to actually plot that lake and its perimeter. Then, if you somehow had a submarine, you could also explore its depth. Not only find out how deep it is, but what's in it there. In this section, this is just what I did. I used a drone or a helicopter to look from high above, and I used a submarine to look into its depth. It might feel a bit rushed because I'm packing it as a section of a very big book, but I really want you to see what trigonometry is about, like I have discovered. So first of all, as you can see in the above diagram, there are the various definitions that I used in trigonometry, some of which I have already mentioned. There is also something called trigonometric identities, and then there are the various laws of trigonometry. And that's what the syllabus teaches us. But it's much more than that. I have already discussed to you the real application of trigonometry in an earlier section. So now I'm just going to talk about trigonometry as a pure mathematical subject. But in that matter too, the current educational syllabus for trigonometry hasn't done justice. So take a look at the diagram below. It starts with the family tree of trigonometry. Trigonometry has a grandparent, that is geometry, the Pythagorean theorem, and the basic definition of sine, cos, and tan. From there, as you can see by the arrow, the parent was born, which are the basic fundamental concepts of trigonometry, ratios and functions, like we have discussed earlier. SOHCAHTOA. From that parent, two children of trigonometry were born. I have shown them as child branch 1 and child branch 2. The first child constituted of what we call the cosine law, sine law, and tan law, while the second branch constitute the trigonometric identities. As you can see, each have different jobs to fulfill, and they are derived from their parents and grandparents, as I've described on the diagram. This might not have left you the wiser yet, but the next part of the diagram will definitely help you map out trigonometry as it is. So take a look at the evolution of trigonometry diagram. It is also related to the earlier family tree diagram, but this one um, talks about the details. So as you can see, at the beginning there was geometry and circle and triangles. Pi was discovered to be the ratio of the circumference by the diameter. This became very useful. The evolution continued to the right angle based trigonometry, where the three sides are denoted by A, B, and C to represent the adjacent, opposite, and hypotenuse, respectively, of the triangle. To find the angles or the side length of any triangle of a right angle kind, if the objective was just to find the value of a missing angle or an unknown side of the triangle, the basic formula of the Pythagorean theorem of a square plus b square is equal to c square was enough. However, as you can see in the diagram, trigonometry evolves to solve the problems of non-right angle triangle. And this is where the sine laws, cosine laws, and the tangent rule were developed. Using this, it was now possible to find the missing angle and the unknown side of triangles even if they did not have a right angle. So in the first avatar of trigonometry, it was about the right angle triangle. In this way, since one angle was 90 degree and the total angle of a triangle is 180, then the remaining two angles is 90 degrees. So the first avatar of trigonometry dealt with 90 degrees. In the second avatar, since there was no fixed 90 degrees, it was about 180 degrees. That was a major upgrade in the capacity of trigonometry. And then in the third avatar of trigonometry, as you can see in the diagram, it became unit circle based trigonometry. Now it was no more about just the unknown 90 degrees or the unknown 180 degrees. It was the whole package, or the 360 degrees. Basically, what was found out is that if you plotted y is equal to sine x on a graph, it would produce a periodic or harmonic curve as shown in the diagram, which makes a full circle after 360 degrees. A similar cycle is made by the equation y is equal to cos x, and there's even a similar cycle with y is equal to tan x, as you can see. Now this opened so many doors that algebra could not enter. Whereas algebra had got polynomial equations, they were not enough to model so many that had periodic or harmonic patterns, like the swinging of a pendulum. So this final avatar of trigonometry became extremely useful for physicists and even economists. Then, by combining trigonometry with algebra and their polynomial equations, you could practically get equations to model almost any physical phenomenons and even economic phenomenons. The equations that would come out would be very complex, and so they needed some tools in the form of trigonometric identities to simplify and solve them. It could be just to find the value of an angle or a side, or it could be to do some derivatives or antiderivatives, whatever the requirement was. So basically, this diagram tells us what trigonometry is all about, where it came from, and where it has taken us. So now I've given you a bird's eye view. Now let me go into the depth of trigonometry by providing you the third part of the diagram. The Venn diagram that I've shown here basically summarizes the evolution and the family tree of trigonometry. So the trigonometry that you and I have studied in school and college is not only the 0 to 90 degree trigonometry that was used by the engineers who made the pyramids in Egypt. The trigonometry that we know today is also not limited to the 0 to 180 degree trigonometry that navigators of the oceans in the times of Christopher Columbus had used to find their way across the oceans. Now, today, we are in the 0 to 260 degree avatar of trigonometry, which includes the periodic or harmonic property of trigonometric functions, which helps us dramatically not only to study pendulum, but even to get electricity in our homes and to get our computers and mobile phones working, and so many other things. The fifth box is a list of various problems that are solved using trigonometry. This might give you a flashback of your teens or early 20s. For those who loved trigonometry, it would have been sweet memories, and for those who hated trigonometry, it would have been bitter memories. Nonetheless, this is not a syllabus. There's no exams for reading my book. Let's just go back and explore what is it that we're actually doing on the subject that we call the trigonometry, and that we either loved or hate. The first type of problem was proving trigonometric identities. This is the first encounter and the lasting memory that we have of trigonometry, proving left-hand side is equal to right-hand side, as I talked to you just earlier. The second type of problems that we were given in trigonometry was to solve for unknowns in the right angle triangle, like finding the height of a tower, a building, or an object, or finding an angle, or the length of the side of a right angle triangle. Then, using the various definitions of sine, cos, tan, and the Pythagorean theorem, along with some trigonometric identities, we are supposed to solve for trigonometric equations and find the value of an angle or some unknown other variables. The fourth type of problem was to graph trigonometric functions on a Cartesian graph and analyze it. This one is not that common, I'm sure, and many of the students wouldn't have come this deep in trigonometry. At this point onwards nears engineering or science modeling problems. But an example is the graph that I provided to you earlier. It is I think the main reason that is that we are not made to plot the graphs of trigonometric functions, that we did not fully comprehend and appreciate trigonometry. The fifth type of problem that we faced in class 11, 12, if you did mathematics, was to solve for non-right angle triangles using the sine law, cosine law, and various trigonometric identities, find the value of the angles or the area of a triangle. Finally, at the greatest depth of trigonometry is the real life application. This is beyond just finding the angle and the height. It's about making predictions, finding rates, effects from calculus. It's used in navigations, harmonics, waves, and everything else I told you earlier on related to physics. So this is trigonometry as it is in its full scope and details. I haven't gone through everything, but I was able to convey my own reconciliation with trigonometry to you. Knowing this much of trigonometry, I feel good. I feel that I have redeemed myself for not having been serious enough in my engineering mathematics course. when I was in my early 20s. There was this lingering thought, what if I had seriously studied mathematics and here trigonometry? I would have loved it and understood it and fulfilled my heart's desire. This what if haunted me all these years. But after writing this section and having researched so much on it, this thirst is quenched. Now this ghost is no more looming over my head. I hope that this section has helped you, like it did to me, to appreciate and love trigonometry as it is. It's not gigantic, that what trigonometry is, but it's not minuscule also. I didn't know that. Now I do. What about you?